Hello and welcome back to the course on deep learning. Today we're talking about max pooling and we've got some very exciting slides coming up ahead and even a special surprise at the very end of the tutorial. So let's get started. The first question is, what is pooling and why do we need it? Well, to answer that question, let's have a look at these images. On these three images, we've got a cheetah. In fact, it is the same exact cheetah. On the first image, the image is positioned properly, and the cheetah is looking straight at you. On the second image, it's a bit rotated, and the third image is a bit squashed. And the thing here is that we want the neural network to be able to recognize the cheetah in every single one of these images. In fact, this is just one cheetah. What if we have lots of different cheetahs? Here's a cheetah, here's a cheetah, here's another cheetah, here's a cheetah, here's a cheetah, and here's a cheetah. And we want the neural network to recognize all of these cheetahs as cheetahs. And how can it do that if they're all looking in different directions? They're all in different parts of the image. They're like, their faces are positioned in different parts of the image. Somebody's on the right hand side, somebody's in the left corner, somebody's in the middle. They're all a bit different. The texture is a little bit different. The lighting is a bit different. There's lots of little differences. And so if the neural network looks for exactly a certain feature, for instance, a distinctive feature of the cheetah is the tears that are on its face going from the eyes, or the shadows that look like tears, the texture, the pattern that is going from its eyes down its on the sides of its nose that looks like tears, that's a distinctive feature of the cheetah. But if it's looking for that feature which it learned from certain cheetahs in an exact location or an exact shape or form or texture, it will never find these other cheetahs. So we have to make sure that our neural network has a property called spatial invariance, meaning that it doesn't care where the features are located. Not so much as in which part of the image, because we've kind of taken that into consideration with our map, with our convolution layer, but it doesn't have to care if the features are a bit tilted, if the features are a bit different in texture, if the features are a bit closer or if features are a bit further apart relative to each other. So if the feature itself is a bit distorted, our neural network has to have some level of flexibility to be able to still find that feature. And that is what pooling is all about. So let's have a look at how pooling works. Here's our feature map. So we've already done our convolution and we've completed that part, and now we're working with the convolution layer. Now we're going to apply pooling. So how does it work? We're going to be applying max pooling. There's several different types of pooling you can apply. There's mean pooling, max pooling, sum pooling, and we'll comment on those towards the end of this tutorial. But for now, we're just applying max pooling. So we take a box of 2 by 2 pixels like that. And again, it doesn't have to be 2 by 2. You can choose any size of box. And again, we'll comment on that towards the end of the tutorial. And you place it in the top left-hand corner. And you find the maximum value in that box. And then you record only that value. And you disregard the other 3. So in your box, you have 4 values. You just disregard 3. You only keep 1, the maximum, which is 1 in this case. Then you move your box to the right by a stride. You select the stride once again. So here we've selected a stride of 2. And that's what you normally select. You can select a stride of 1, you can select, so there are overlapping boxes, you can select any kind of stride that you like, even 3 if you want, but we're selecting a stride of 2 here, and that's what is commonly used. And then you repeat the process, you record the maximum. Here, if you cross over, it doesn't matter, you just continue doing what you're doing, so you still record the maximum here, 0. Here the maximum is 4, here the maximum is 2, here the maximum is 1, 0, 1, 0, 2, and then 1. So as you can see, a few things happened. First of all, we still were able to preserve the features, right? The maximum numbers, they represent, because we know how the convolution layer works, we know that the maximum or the large numbers in your feature map, they represent where you actually found the closest similarity to a feature. But by then pooling these features, we are, first of all, getting rid of 75% of the information that is not the feature, which is not the important things that we're looking out for. Because we're disregarding 3 pixels out of 4. So we're only keeping 25%. And then also, because we are taking the maximum of the pixels that or the values that we have, we are therefore accounting for any distortion. So for instance, two images in which, for the example, the cheetah's tears on the eyes are, in one image they're a bit to the left or a bit rotated to the left, and in the other one they're a bit, and they're how they're supposed to be, or how we, like if we take one as the basis and then the other one they're a bit rotated to the left, the pooled feature will be exactly the same. So you can see here, if we are talking about the cheetah's tears, then let's say this is the 4 and this is where it was here. Then if it was a bit rotated, so for instance the 4 ended up over here, then when we're doing the pooling, we're still going to get the same pooled feature map. And that's kind of the principle behind it. It's a very rough explanation, again, intuitive explanation, but that's the point of pooling, that we're still being able to preserve the features and moreover account for their possible spatial or textural or other kind of distortions. And in addition to all of that, we're reducing the size. So there's another benefit. So we're preserving the features, we're introducing spatial invariance, we're reducing the size by 75%, which is huge, which is really going to help us in terms of processing. And moreover, another benefit of pooling is we're reducing the number of parameters. So we're reducing, again, by 75%, we're reducing the number of parameters that are going to go into our final layers of the neural network. And therefore, we're preventing overfitting. It is a very important benefit of pooling that we're removing information, and that is a good thing. That is a good thing because that way, our model won't be able to overfit onto that information, especially because that information is not relevant. Remember, like at the very start, we were talking about, even for us as humans, it's important to see exactly the features rather than all this other noise that is coming into our eyes. Well, same thing for neural networks. By disregarding the unnecessary, non-important information, we're helping with preventing of overfitting. So there we go. That is what pooling is about. And the question here is, of course, why max pooling, right? There's lots of different types of pooling, and why a stride of 2, why a size of 2 by 2 pixels, lots of all these things. And on that note, I'd like to introduce you to this lovely research paper called Evaluation of Pooling Operations in Convolutional Architectures for Object Recognition by Dominik Scherer from University of Bonn. There's the link. And the beauty about this paper is that it's very, very simple, very straightforward. So if you've never read a research paper before, but you'd like to give it a go, this is a great place to start. It's very short, only 10 pages, very easy to read. And plus, the extra benefit is that now that we've discussed convolution and pooling, you will be totally comfortable with everything that they're talking about in this paper. And this is a great way to actually reinforce your knowledge. So I highly recommend checking this paper out. It'll take 20 minutes to read it. And you can even skip part 2, which is called related work. If it feels a bit far-fetched or alienating, just don't read that part. Just go straight from part 1 to part 3. And the one thing that you do need to know about this paper, they talk about a concept called subsampling. Well, subsampling is basically average pooling. So remember how here we were taking the maximum. So in our square, we were taking the maximum value. There's a concept called mean pooling or sum pooling. Sum pooling is you just sum these values up. Average pooling or mean pooling, you take the average value out of all of these. And subsampling is kind of like a generalization of mean pooling. It's a more kind of generalized approach to taking the average of these values. And you can read a bit more about it in the paper, but otherwise just think of it as average pooling when you're reading that paper. And so that's where you can get some additional information on this topic. And now kind of let's recap. Where have we gotten to? So there's our input image. Then we applied the convolution operation and we got the convolution layer. And now to each of those feature maps that we get, we've applied the pooling layer. So we've done these 2 steps, convolution and pooling. And now we're going to do something very fun, something exciting. We're going to experiment with this. So this is a screenshot I took from a tool created by Adam Harley from back when he was at Ryerson University of Computer Science, and now he's at Carnegie Mellon, I think, doing his PhD. And a great tool. So let's open up. Let's have a look. So you can find it. You can't actually find it through Google. You have to know URL. It's just hard to find it through Google because there's no text here. Well, just this URL, scs.ryerson.ca, and then this stuff on the end. And basically, this is exactly what we're doing, but visualized. So here, you need to draw a number. So let's say I draw a number 4. And this tool will put the number 4 here. That's your image in our first step. Then this is the convolution step, right? And this is the pooling step. And also pooling, by the way, is also called downsampling. So pooling and downsampling are the same things. So you can see it's applied convolution, then it's applied pooling, and you can see how it exactly works. So you can see what kind of convolutions it has applied, or what kind of filters it applied, what they look like. You can see what features it's looking out for. And then it's applying pooling, so it's reducing the size. And you can see here that this is important, right? So you can see that this is the convolved image, and this is the pooled image, and you can still see the same features. It's just less information, but same features, right? The features are preserved. That's the important part. And moreover, if our 4 was a bit to the kind of like rotated a bit to the side, it would still be able to pick up very similar pooled layers. And then after that, it's got more layers. We haven't talked about that yet. So then it's got another convolution layer here, which we actually won't have. And then it has another pooled layer, but it's basically just repeating that same process. And then after that, this is what we're going to be talking further down in the course. It's got the fully connected layers and so on. But you can definitely play around with that. So if I delete that, if I draw a 7, you'll see that it actually tells you the guesses. It guesses that this is a 7, and the second guess, the second likelihood is a 3. So you can draw it some challenging things and see if it can pick them up. So let's say if I draw something that looks like a 0, but it's not a finished 0, will it pick it up? No, this time didn't pick it up. It looks like a 9 to the image. What if I kind of like finish it like that? See, now it thinks it's a 0 or a 9. And you can see over there what's lighting up, the 0 or the 9. But we'll talk about that part further down. Let's do one more. Let's say like 8. I think 8s are pretty hard for this. No, picked up an 8. So you can see that goes into an 8. And then like after that, it stops being recognizable. It stops making sense to us humans, right? These features that it's working with. But at the same time, it is correctly recognizing that it's an 8. Yeah, so definitely play around with that. You can draw a smiley face, see what happens then. Looks like a 3 to this tool, because the tool is obviously trained up only on digits from 0 to 9. So it has to recognize something there out of those, and it recognizes a 3. It's like in life when you see something like a type of fruit that you've never seen before, like a custard apple or something, and you think that it's a pear, because you've never actually seen one before. You don't know what to classify it as. Same thing here. So it hasn't actually trained on smiley faces, and that's why it thinks it's a tree. It's a 3. So there you go. It's a very powerful tool. It'll be helpful for you to play around with it. Actually, when you put your mouse over a pixel, it shows you where the feature detector was to pick up that pixel. So you can see where this pixel is coming from, and also, so you can see how the filter was kind of like going through the image, exactly how we talked about in the course. And here you can see the pooling. You can see that the pooling is done with a little square size of 2 by 2, and you can see that it's a stride of 2 as well, just as we discussed in today's tutorial. So there you go. Have a play around with that, and I hope you enjoyed today's session. I look forward to seeing you next time, and until then, enjoy deep learning.